All right, let's do a quick review of factor groups and normal subgroups. We've talked about cosets of subgroups, and now we're going to talk about a special kind of subgroup whose cosets have some very nice properties. So here we have a subgroup of a group is normal if GH equals HG for all G in G. So remember this H is a subgroup, and GH means take the element G, multiply by every element in big H. In particular, big H has the identity, so this set has G in it. Also, HG means take every element in the set H and then multiply on the right by G. Now this element also has G in it. Do you see why? It's the same. This also has a little G in it.
Right, because H is a subgroup.
Yeah. So H has the identity. So that's right. So we know that these two have the element G in common, but that doesn't mean they have all elements in common. So a subgroup is normal if these left cosets and right cosets have all elements in common. And you have some examples. Here in this case we have S3, and we have a subgroup consisting of the elements 1 and 1, 2. And here you say if we take this element 1, 2, 3, which is an element of S3, times the set H, where H is just the elements 1 and 1, 2, you get this result. But if you multiply on the right, you get a different result. Okay, so that's kind of the idea. So in this case, this left coset is not the same as this right coset. So big H is not normal. So to show, we've seen this kind of thing before, to show something is not normal, you just need to show one case where it fails. To show that it is normal, you have to show all the cosets are the same left or right. So in this case, we have another subgroup of S3 and that has two cosets, and those two cosets are the same left and right. So this one is normal. Now, what was I going to say? So recall also the relation between size of the subgroup and number of cosets. So for instance, this subgroup H had two elements, and it's a subgroup of S3 which has 6 elements. So how many cosets are there? If you have a subgroup of 2 elements in a group of 6 elements, how many cosets are there?
3.
There's 3 cosets. We didn't show them all here, but there are 3. Right, one coset has to contain the identity, which is H. So H is one coset. This is another left coset, and then there's one more. All right, so good. So let's go here. So this is all kinds of stuff with cosets. And you go down, down, down. And there's some things to prove here. I guess we didn't get here. This is an interesting one. This one says that if G is a group and H is a subgroup of G with index 2, then H must be a normal subgroup of G. Which is kind of interesting. Now, do you remember what index 2 means?
I was actually trying to look up the definition, but it's not in this chapter.
Index 2 means it has 2 cosets.
Okay.
And you write index, the way you write index is, maybe I should move this over there so we can switch over. Where's my mouse? Doesn't want to go. There we go. So if H is a subgroup of G and the index of H in G is the number of cosets of H in group G. Okay. So the index is written as this way, G colon H. I think it's G colon H. It might be H colon G, but I think it's G colon H. So we have the equation. So from Lagrange's theorem, we have a formula for this. It's, in fact, you can get the number of cosets from the order of G and the order of H.
Right.
So do you remember what that is?
You would divide it.
Yeah, take the order of G, divide by. So that follows from the little g's. Here. Whoops, and that's not little g. Okay, so let's continue. All right, now, then this one says, prove any subgroup of an abelian group is normal. And then I think that's pretty straightforward. I think the hard thing about this may just be to give the right words. I mean, the idea is that any left coset, HG should be equal to GH. And just say that in words in the right way. I should say that I think that what people probably need most work on is proofs. And I think that, as I wrote to you in an email, that it would be good to go back over past proofs that were assigned and just don't look at them and write them up again. And you can send them to me so I can critique them. I think that's really the only way you can get to be better at proofs is have them critiqued. So I think that would be a good thing to do.
Now on 14.4.8,
Yes.
that's set difference, right?
Yes,
Okay.
that's that difference. G not H. That's everything in G that's not in H.
Okay. So I was making a little side notes.
Okay. All right. Now this proposition 14.4.10 is slightly different from the condition that HG equals GH. It's quite similar, but it's slightly different. It says let H be a subgroup of G. Then H is normal if and only if every left coset of H is also a right coset of H. Now, if you say GH equals HG, that's showing that the left coset GH is the same as the right coset HG. But that's not quite the same as saying that every left coset of H is also a right coset of H. In fact, you can say, in fact, that shows one way. That does show one way. That shows that this condition, this definition here implies this definition down here. Because if GH equals HG for all cosets, then that means every left coset is a right coset.
Right.
But you don't immediately have the other way around. So what you need to do to prove this one, 14.4.10, is say, suppose every left coset is also a right coset. And then you need to prove that GH equals HG for all elements in the group.
So that part is pretty much the first part of the proof, and then you would do the converse of
Yeah.
it.
Well, yes. I mean, I think the first part of the proof is simple. It's relatively simple. This definition, 14.4.1, implies 14.4.10 directly. It seems to be a stronger condition.
And it's just reworded.
Well, I mean, see, the thing is that this one says GH is this specific right coset. Definition 14.4.1 is very specific. It says that if I have a left coset, then it's equal to this right coset.
Right.
Now, 14.4.10 says every left coset is a right coset. It doesn't say which one.
Gotcha.
All right, so this one is less specific. It's just a little bit. It's about the same, and you just have to think. It's really don't overthink it. I mean, the idea is GH. According to this, GH is a right coset. Which right coset must it be? So don't overthink it. It shouldn't be a very involved proof.
I normally do.
Yes, I know. No, and you're not the only one. All right, now here's another very useful characterization of normal subgroups, and I apologize for the misprint here. This should be a theorem. It says, let G be a group, and N is a subgroup of G. Then the following statements are equivalent. N is a normal subgroup of G, and for all group elements in the entire group, G and G inverse is contained in N. All right, so you take any element of big N, take any element, and multiply it on the left by any element of the big group G, and then on the right by element G, by the same element G inverse, and you get that another element in the subgroup. That's a little bit hard to follow, and we'll see some examples down below.
Well, it makes sense because in order for it to be a subgroup, it has to have an inverse. Correct?
In order for N to be a subgroup, it has to have an inverse. That's true.
So obviously N is going to be within N, and N also equals N.
Well, remember that N is a set. It's not a element.
Right. But take like real numbers, for instance.
Right.
Real numbers is inside of real numbers.
That's true, but you can map real numbers to real numbers so that you don't get all the real numbers. For instance, you can take absolute value of x, and that maps the real numbers into the real numbers, but not all of them.
Right.
So what this is saying is that if you take this subgroup and you map it by multiplying on the left by G and on the right by G inverse, you get that same subgroup back again.
Okay.
And there's a proof down here, and I think I talked through that in the video, and so, but I want to get the ideas first. So let's see. Are there some good examples of normal? I'm trying to think of a good example. Let's see. Well, actually, I can think of an example from linear algebra. No, I can't think of an example from linear algebra, so forget about that. Okay. But the thing is that you've seen things like G, and G inverse in linear algebra when you do change of basis. When you change basis of a matrix, you see some things like this.
Right.
But it's not exactly the same, because when you're changing basis, you're not multiplying a set. You're only multiplying a particular matrix. So it's not exactly the same. So I can't think of any good examples of normal off the top of my head. But all right, maybe I can think of one example. Suppose you take any dihedral group. Right? Now dihedral groups have rotations. Sorry, I just don't have my tablet again. They have rotations and they have flips. Now you know that if you take one flip and followed by another flip,
It'll wind up in the same spot.
in the same spot. But if I flip over one axis and then I flip over a different axis, I'll end up with a rotation.
Right.
Right.
Because it's like a Rubik's Cube.
It's like a Rubik's cube, yes. So in fact, if I let N be the group of rotations, the subgroup of rotations in the dihedral group. So for instance, let's take the square. Let me write this out. So let's do example of normal subgroup. Take G equal D. I think we write D4 like this, right? So that's the dihedral group. This is symmetries of a
I
square.
thought it was a subscript.
All right, well. Okay.
I may be wrong.
You know, I think you're right. Symmetries of a square. Okay.
Yes.
Okay. All right. So let's take H. H is equal to the rotations. Now remember that the order of G is what? How many elements in that group?
Four.
Well, how many rotations and how many flips?
Oh,
Here's a square right here.
Symmetry. I know. I'm trying not to.
No, I mean a square. You can manipulate it. Right. You can rotate it,
Well,
or you can flip it.
Rotate it or flip. That's
Yeah.
6. No.
How many flips are there?
There's 4 on each side. So 8. 8?
8. I can flip it across here, like that. I can flip it across diagonal. I can flip it across this diagonal, and I can flip it here. So there are 4 flips. So the dihedral group 8. The D4 has 8. And how many rotations are there?
There's quite a lot.
In rotations of a square?
Well, the square.
Yes.
I was thinking cube. for some
No,
reason.
no, not cube. No, we're not there yet.
1, 2. Would it go backwards, or would that still be?
Well, you have to think that a 270 rotation is the same as a backward 90. Right?
Oh,
So
yeah,
you
that's
don't
true.
want to double count.
So just 2.
Well, all right. So you take your notebook. Let's start here. Right? No, this should be a square, right? That's 1.
So there's 4 rotations.
There's 4 rotations. So the rotation group has order 4. 4 rotations. Okay, and then let's think about this. So suppose I take a rotation. So take any rotation. I'll call H, and then multiply, and then take any element of G. So there are 2 cases. Okay. So case 1 of G is a rotation. Here, I shouldn't say take any element of. I shouldn't say take any rotation H. Let me take this out. Now, if I G is a rotation, then if I take G times H times G inverse, and where H is a rotation, right, if H is a rotation and G is a rotation, what about GHG inverse?
No, it just equals H.
No, it doesn't. Not necessarily. No, it does. You're right. You're right. It does equal H. So it's also a rotation. You're quite right. Okay? Because the rotation group is commutative. So that's true. All right. Now case 2. G is a flip. All right. So then if H is a rotation, I'm going to copy this.
So if G is a flip, but would H still be a rotation?
Well, that in the definition of normal, remember, definition of normal is that we're looking for the question is G, H, G inverse equal to H for all G in G. That's the question. So you're choosing a specific G, and then you want to check all rotations and see if it's still a rotation.
Well, I would think so.
All right, but all right. Now GHG inverse. Well, here let's think about this. Suppose my G is 90 degree, and my flip is just flip around this axis. So here we'll use yours. Right. Okay.
So it's just
So-
a flip,
That's a flip. So G inverse would be the same, right?
right?
And then rotate, and then flip. Actually, you should have started with this head up like this. So flip this way, and then rotate, and then flip this way. So what
Well, the
happened?
orientation changes.
Well, what's the net result? We started here, and we ended up here.
So 270 counterclockwise.
Apparently 270 counterclockwise. Now, if you did a different flip, you'd end up with a different thing, right?
Right. So if we did the...
If I did this flip here, how is this going to do? This flip,
against the y-axis.
this flip would mean exchange those two, so that would be like this. That would be this flip. And then I do the rotation. Then I do the same flip again, which would be exchange these two. Well, what do you know? It's still 270. I don't think that's always true. It may be, but I don't I think it's always true. In fact, I think I must have made a mistake because that can't possibly be true. Or it could be. It could be.
Well, if it is, there's probably a theorem.
All right. Well, anyway, so I should say GH inverse is also rotation, but not necessarily equal to H. All right. So in both cases, no matter whether G is a rotation or flip, it's always true that G, H, G inverse is a rotation as long as H is a rotation. Okay? And this means that G, H, G inverse. Actually, this means that GH inverse is, basically it says that GH inverse is a subset of H, right? Because we didn't say it was equal to H. It shows it's a subset.
Right, but can we not use the...
Yes, then you use what we just talked about.
There was a proposition for it.
Yes, it's right here. It's this proposition 2.
Right. But there's also proposition 3 that says it's equal.
Well, what you showed that this condition is satisfied.
Oh, we were only showing the second one.
You show this condition is satisfied, and here it says these statements are equivalent. So as long as you show any one of these things, as long as you show any one is true, then the others are all true. Right, then this is the easiest one. This is always the easiest one.
Okay.
I mean, it's harder to show that it's equal. So this is the easier one. Okay, and the theorem implies that H is a normal subgroup. Okay. All right, so that's one example. So you pointed out Rubik's Cube. This is all very closely tied up with Rubik's Cube. But let me not go there right now. Okay. All right. So here it says the intersection of two normal subgroups is also normal. And then here it says, all right, this one's interesting. We can talk about this one afterwards. Some other properties of normal subgroups. The upshot is this. If a group G has exactly one subgroup H of order K, then H is normal in K. So if you have a group and there's only one subgroup of a certain size, that subgroup is normal. Okay, so that's a neat thing. All right, then let's see. And then this one says, let's see. All right, and this one says basically, so the upshot is this: that if you have G1 and G2 then you also have G1, G2, right? G1, G2 is also an element. So the question is, right, so here's given G1. Okay, I'm in the wrong space here. I have to get out of the, I guess this will do it. And there we go. Given G1, G2, in G. So the question is, what is the relation between the cosets? I have a coset G1H. I also have a coset G2H and G1, G2H. All right, and the answer is if I take any element in G1H and multiply by any element in G2H, then I get an element in G1, G2H. But there's a condition here. I can only guarantee this, if H is normal. If H is normal, then if I take an element in one coset and multiply by element in a different coset, then I get an element in the product coset. And what this enables you to do is it enables you to define a multiplication of cosets. In the case where H is where H is a normal subgroup. All right, so we can draw. I don't know if we can draw a good picture, but we can try. All right, so here's my one coset, and here's my other coset. And then here I'll take a point here and a point here. So this coset here is G1H. G1H. Is G1H, and then this one here is G2H. And then I'll draw another one, which is G1, G2H, which is off here somewhere. I should have made the cosets different colors. So this coset here is G1, G2H. Whoops, I didn't catch it. All right. So the point is that a point in here, a single point in here would be an element, G1 little h1. That should be a small g. All right, this particular element is G1 h1. Then I have a particular element here, which would be G2, H2, because the H's are not necessarily the same, and the G's are not the same. Right? And then I get another element here, if I take G1H1 times G2H2, whoops, sorry,